Okay. Okay, so hello everybody. So we are happy to welcome today Frédéric Marin from the Observatoire de Strasbourg. So Frédéric defended his PhD in 2013. He then did a postdoc during 3 years in Czech Republic. And then he came back to Strasbourg for a postdoc first, and then he has been hired as a chargé de recherche at the CNRS. And Frédéric is an expert of high energy sources, and in particular in the polarimetry, multi-wavelength polarimetry of high energy sources. And this is what he will present us today. So Alex, thanks a lot.
I don't have a laser pointer. So, oh, if this works. No, it doesn't. But I have one in my bag. Sorry, I forgot. Very brief. All right. Thanks. So thank you for coming, and thank you for everyone who is listening to this presentation. So I will give a presentation, and basically it's a review of the 2 years of activity of the very first X-ray polarimeter that has been launched in space and which is dedicated to X-ray polarimetry. So I'd like to start this presentation by a little quiz, a test. I strongly would like to know if anyone can cite an X-ray or a gamma ray satellite. Or see, that's so easy. Everyone knows many of them. I don't have to cite them. But not the same question. Who can tell me the name of a past mission which is dedicated to X-ray or gamma ray polarimetry? Things are getting a bit harder, indeed. And there is a reason for this. You can see here the past instruments. And as you can see, all the pictures are in black and white. And one is a military rocket, and 2 are solid block satellites. So it tells you that this happened a long time ago. And in fact, if you look at the temporal evolution of X-ray satellites, including polarimetry, those are the one in red, as you can see over time, well, basically there has been none, almost none of them. If you put it in more chronological order, from the discovery of X-ray radiation, you see that the first X-ray experimentation to detect high energy light from cosmic sources took place in the 60s, using basically rockets or instruments that were high in altitude. And we measured the X-rays from the sun and from Scorpio 6-1 in 1962, which basically was the start of X-ray astronomy as we know it. And in fact, after that, there had many X-ray missions, X-ray and soft gamma ray missions, even hard gamma ray missions. But on the bottom part, you see the same status for X-ray polarimeters, and there have been non-gamma ray missions dedicated to polarimetry. So the X-ray mission were actually flown just 10 years later the discovery of X-ray emission from Scorpio 6-1. And there were Bragg crystals mounted on the satellite Ariel 5 and also at the A-Solar Orbiter mission. And after that, basically, there has been nothing. Over the years that those 2 missions walked, they measured the polarization in one source, the Crab Nebula, with 13 sigma confidence level, and just a few upper limits on other sources, including Scorpio 6-1. So the reason why is because those satellites were not sensitive enough. The Bragg crystals are very big pieces of crystals, and you need a lot of them in a circular shape. You need to rotate them. They are heavy. They are sensible to only one energy, basically it's 4.5 keV, plus or minus a few eV. So it's a complicated technology. It's heavy, so it's expensive. And after that, it was basically a big void. Integral was launched, and they made since then, some soft gamma ray polarization measurements for a few sources. But the problem is that this mission was never dedicated to polarimetry, so it was never calibrated on the ground. So the measurements, which are informative, cannot be completely trusted. And after that, there have been a few, one or two missions, including big air balloons, and then the launch of the mission that we will discuss, IXPE. So the question you may ask yourself is why? Why is it so complicated? Why is there why was there 40 years, almost 40 years of nothingness? Well, usually there are three counter arguments to X-ray polarization, and it's basically the same for gamma ray polarization. First, it needs rotation. You need movable part, because to measure the property of light using the Stokes parameters, you need to rotate your instrument to measure basically the orientation of your electric vector field at different angles. So it needs to move, and everything that moves in space is not very much reliable in terms of resiliences, and it's expensive. The technology is less advanced than spectroscopy, timing, and imaging. Of course, there has been 40 years of non-development, so of course there is a technological gap. And also, polarized flux are often much lower than total fluxes. This is logical. The polarized flux is just the multiplication of the polarization degree and the total flux. And the polarization degree ranges from 0% to 100%. So at best, you have the exact same total flux. And in most of the case, you have 1/10, 1/100th of the total flux. So you need to integrate much, much longer. The two first arguments have been recently discarded, because in the beginning of this millennium, our Italian collaborators developed a completely new way to measure polarization. Before, we used Compton scattering and Bragg crystals, so scattering parameters, and there were big block of siliciums or other elements like that. But using the photoelectric effect, those colleagues developed this gas pixel detector. It's actually a very cheap instrument that is extremely small, very compact, very resilient. It's 2 by 2 centimeters. It's nothing it costs basically nothing. And you can step on it and it still works. So it's not that bad, but don't step on your satellites. How it works is actually very bright. There is your incoming X-ray photons. There is a window made of a very specific plastic that just simply reflects the optical, UV, and other energy photons. And then you have a gas inside, which is inside a chamber. And this gas basically will interact by photoelectric effect. There will be photoelectrons that will be emitted by the incoming X-ray plus an Auger electron. And the secondary photoelectron will create tertiary photoelectron, and so on and so on. And all those photoelectrons will be captured by a pixelized anode on the bottom. And what is truly remarkable is that the information of the polarization from the incoming X-rays is conserved, because the direction of emission of your photoelectrons is proportional to the polarization, the incoming polarization. So even though you have the photoelectric process, you keep the information of the initial polarization. And this is basically what you get on the pixelized anode. You have the impact site, and then you have a trace where energy is deposited as more and more photoelectrons are created. And the direction here, we constructed from the barycenter and the point of impact on your detector, gives you the polarization angle. What you do is you collect many photons. You see how, if all of them have the same direction for the trace, and you integrate over 360 degrees. And what you get is this modulation. The larger the amplitude, the bigger the polarization, because it means they are all going in the same direction.
So for an individual event, you see you get a track for the electron.
Sorry?
For an individual event, an X-ray coming in, you see the track of the electron.
Of the Auger electron?
Yeah.
The Auger electron, we can see it. We can record the direction of the Auger electron. Yes, we are using it when we reduce the data to be sure about the direction of emission of the first photoelectrons, because they are basically along a parallel line, and they are most of the time emitted in the opposite direction. So it helps us to reconstruct the track, this Auger electron.
But it sort of ionizes something, and you see the entire track, or
no, the gas itself is a very specific mixture that only react at very specific energies. So you don't have a full ionization track, so you don't have many disturbing effects. And when you have if you have ionization of your gas, if you get photoionized electrons, photoionization, the photoionization is by essence non-polarized. So it will not, it will be inside the background here. I'll show you the background just after. This is what I meant. What's happening is that you have your modulation, and the bottom on your modulation curve, you have this parameter A, which is the background. This background is all the unpolarized photoelectrons and instrumental effects inside your detector, because all the scattering inside the detector will also be canceled out. The polarization is completely random. So what you do is that you simply cancel this term in your calculation, which is below here, and you get the modulation. It's extremely easy, and you have zero instrumental polarization here. So it's a perfect detector from this point of view. And you can see clearly the difference between a fully polarized signal and a completely unpolarized signals. It's only noise here. So these two first problems were solved, basically, because it's extremely sensitive. It's 100 times more sensitive than what's made in the past. And there is no need for rotation, because you electronically integrate your signal. That's all. You don't turn your detector. So now the problem is the observing time, and this will remain. This is the doomed question for X-ray polarization, or basically for polarization, whatever the wavelengths, because it relies on a very specific parameter called the minimum detectable polarization, which is the level over which you can reject the hypothesis that your signal is fake at 99% confidence level. And it's completely related to the background noise, the source flux, and the time of integration, plus a modulation factor that is the quantum efficiency. And basically, how does it translate in X-ray polarization? Well, in X-ray astronomy, if for a source detection in X-rays, which let's say XMM, you need 10 counts, you know that there is an X-ray source here. For measuring the spectral slope, a Paolo 100 count will be enough to have a rough idea. But if you want to get 1% MDP, so you are sure you will measure a polarization degree that will be higher than 1%, and you are absolutely sure it is real, then you need 700,000 counts. So as you can see, it's tremendous. For this very much reason, we couldn't rely to put a polarimeter on board of Athena or whatever other missions. We need a dedicated instrument. We need a dedicated mission that will do only this, measure the polarization. And actually, as you can see in the X-rays, there are many, many things we can do. Acceleration phenomena, emission in strong magnetic field, scattering in aspherical geometries, and fundamental physics. I will briefly show you the results for all of them. And in X-rays, in the soft band, most of the time you have absorption. So it's very hard to measure something. Between 1 and 10 keV, most of them are strong emitters. There is not so much absorption. And the Paolo is still, even though it's decreasing with the energy, it's still plenty of photons that you can get. And larger energies, higher energies than 10 keV, it's becoming difficult because the signal is more and more faint. So basically what happens is that we worked with the NASA, and we built between the Italian Space Agency and the American NASA, the IXPE, the Imaging X-ray Polarimetry Explorer. It's the first ever mission that is completely dedicated to X-ray polarization. It was launched. Oh. So for those who are listening to us, there is the fire alarm here. So c'est un exercice, hein?
Okay, sorry. For people on Zoom, there is a fire alarm.
So yeah, we will be back after the fire alarm. I'll leave you with the video. It's entertaining.
And the noise of the
Sorry, I was muted. So basically, you had the time to read the parameters on the performance of IXPE. I just want to summarize that with this instrument, you can do imaging, spectroscopy, polarization, and timing, all of them. So what we did is that we observed all sources in the skies that were bright X-ray emitters, with the exception of the sun, because it's so bright it will destroy the detector. So this is the only source that we haven't yet observed, and it will be the last source, the champ du cygne of the detector, when we will burn it in the atmosphere. We will burn the detector first by looking at the sun. We did commissioning, we did some calibration phase and tests for the first few weeks. And in January, we started the observation. So this is not in chronological order. It's in a random order, what I will show you. But let's start with the magnetars. Magnetic field, especially when they are very high in space, would be a natural precursor for creating polarization. So we expected high polarization from basically all magnetically dominated sources. And one of the sources we wanted to observe very much was those what we call a magnetar. So in the magnetar theory, you have a neutron star with extreme magnetic field, usually in excess of 10 to the 13 Gauss. This is a magnetar. And there has been for almost 90 years a theory called vacuum birefringence by Heisenberg and Euler in 1936. It's extremely important for the QED. And there is a QED effect linked with the fact that for a very high magnetic field, you expect the quantum vacuum to become birefringence. So basically, you have virtual pair of photons and of electrons and positrons that are created, and they will basically briefly interact with their environment and disappear. But the thing is that if you have a very, very strong magnetic field, the optical path of the ordinary and extraordinary light will be different. So basically, we will create polarization. The vacuum will by itself create polarization when there will be a photon coming from the source to the observer. And this effect is expected to be extremely strong. In this spectrum, you see the phase of your object, two phases. On the top, the total flux, and you see the kind of pulse shape you expect from your model at different energies, or almost all of them within the IXPE energy band. And on the bottom spectrum, you see the expected polarization here, the polarization fraction between 0 and 100%. And what you expect is that you are between 80 and 100% polarization due to the quantum birefringence effect. It's extremely important to prove or disprove its existence because it's a strong cobblestone of the QED paradigm, and basically our understanding of the unified model, the standard model for physics. So what we did is that we observed a magnetar, which is this name for you something, for 840 seconds. And it's expected to have a very large spin-down magnetic field of the order of 10 to the 14 Gauss, so higher than the limit for the QED effect to appear. And we integrate the polarization, and we found 12% at 48 degrees, between 2 and 8 keV. You see the different detector units measurements here with the cross on the spectrum, and the sum of them plus the sum with the spectropolarimetric fit by IXPE. Well, we are very, very far from what we expect from the quantum birefringence. So we are only at 12% instead of 80, 90%. So in this source, clearly, there is no trace of this QED effect. It's a bit annoying because, well, we should expect something at least more than 40%. But what we have done is that the source is so polarized, 12% is still very high, and so bright that we were able to do some spectropolarimetric analysis. And what we found is that between 2 and 4 keV, the polarization degree in violet is about 40%, with 48 degrees polarization angle, so the direction of vibration of the electric field vector. And between 4 and 5.5 keV, there is no detection of polarization. It simply disappears. It's below the detectable limit, nothing. And after, at the high energy band of IXPE, 5.5 to 8, you have 40%, 41%, with a different polarization angle. And as you can see in this plot, there is a 90-degree rotation between the soft and the hard band of IXPE. The polarization degree is changing a lot. And if you try to analyze that in the resonant Compton scattering scenario, which is basically the scenario that is the most used to explain the emission of X-rays around magnetars, not the only one, but it's probably the favorite one. You have thermal photon from the Coolidge star's entire surface that is emitting and in the soft X-rays, and it's Compton upscattered in the hard X-rays in a twisted magnetosphere. With this model, you expect the X mode at high energy to be of the order of 35%, and this is what we observe, 41% plus or minus 4. So we are within the limits, fine. But the O mode at low energy, so the O mode is different by 90 degrees to the X-ray X mode, ordinary and extraordinary mode. You either have a low, very low polarization, like much less than 10%, if you have a condensed surface, a very thin layer, or you are much higher than 50% in the case of a gaseous atmosphere, much larger and heated from below. And we don't find that at all. So basically, the resonant Compton scattering scenario is good to explain part of the data, but not the other part of the data. And we look at the time, the phase dependence of the flux, the total flux, the polarization degree, the polarization angle. What is interesting is that the spectral shape does not vary with the rotational phase of the magnetar. So basically, this is a scenario when you have a very small hotspot that is rotating as the magnetar is rotating too. So being hidden, visible, hidden, visible. It's not the case. It's not a very small polar region. The polarization angle, as you can see, varies between 35 and 65 degrees, which means that there is some kind of extension of the emission region, but it cannot be fully extending over the whole magnetar surface. Otherwise, because of geometric effect, it will cancel out and you will get zero variation in polarization angle. So it's not a small dot on the surface. It's not a full surface. It's something in between. And in fact, using 3D simulation, the team was able to find a satisfactory scenario to explain this emission in the case of if you have a hotter belt that is on the surface of the star, but only close to the magnetic equator. So a belt around the magnetar. It's extended, but not too much. And with this, you can reproduce the expected polarization degree in the in the low and high energy band of IXPE, the 90 degrees rotation. But it's very preliminary because this scenario has been just invented to explain the data. It needs further and deeper explanation. But it is true for all magnetars. So we observed another magnetar, one axis, and also this one has a dipole magnetic field strength well in excess of 10 to the 14 Gauss. We observed it, and in this case, we found a polarization degree, which is about 20% in the small at the low energy band and 80% in the high energy band. But there is no rotation of the polarization angle in this case. So clearly, the emission region, the geometry of the emission region is different between the two magnetars. So it also means that, well, there is something we need to explain why the two similar objects would have completely different emission, not mechanism, but emission regions, geometry, and topology. Here, basically, you would expect this kind of signature if the surface temperature is not homogeneous and you have a hotter cap covered by a gaseous atmosphere. So, as you can see, we need further investigation, but in all cases, we cannot prove at all that there is this vacuum birefringence, as we expected. Then we looked at another object, which also shows strong magnetic fields, and those are blazars, basically active galactic nuclei, whose jet is pointing directly at us. So we are within the beam. It's highly collimated, it's bright, and it's usually very bright from the radio to the hard gamma rays. But the problem is that how do you, in this jet, how do you energize the radiating particles? How do you do that? We don't understand yet. There is many unknowns, such as the ratio of matter-antimatter, why is there a diversity of emission within the blazar classes? Some of them are called high synchrotron peak emissions, some of them low synchrotron peak emission, depending on where in the spectrum the synchrotron peak is peaking, in the infrared or in the UV. And also what is the order of the magnetic field, and basically its direction with respect to the observer. And the mean direction relative to the jet axis or the observer can be probed by polarimetry because it's a geometric constraint. There are many models to explain the mechanisms responsible for X-ray and gamma ray emission in jets. Very simple models from the beginning of the study, such as one single zone model. So you have a constant density model, constant density jet with the same magnetic field line from the base of the jet to the end of the jet. And you have emission of photons at all energies happening everywhere, very basic, but it gives some first order predictions. Something a bit more worked where you have turbulent magnetic field with reconnections inside the jet. You have also energy stratified models where the emission is not all along the jet, but at very specific portion of the jet, depending on magnetic reconnections or shocks, let's say. So all of them have very specific signatures, all those models, and they are older than that. So which one is the correct one? So this is what we would expect for those different models in terms of polarization as a function of wavelengths. So the chromaticity, does it increase with energy or not? Variability in terms of polarization, you know that blazars are typically variable in total flux in photometry, but also in polarization, some of them within a few hours, days, some of them within a few days, months, and some other more than a month. And the polarization angle, because when you measure the polarization angle in the radio or in the optical for blazar, it has a certain direction with respect to the jet. It's aligned, opposite, or random. So what we have done is that we wanted to determine what is responsible for the X-ray emission in jets, in blazars. We observed Marin 501, one of the brightest sources in the skies in the very high gamma ray regime. We looked at it twice with the 100 kiloseconds, almost twice. And what we found is that the polarization degree is about 10% with a very specific angle that is parallel to the radio jet. Interesting. We also had the same measurement at the same time with different instruments from the millimeter domain to the optical. And what we found is that the polarization degree, shown here, is increasing with wavelengths. So there is some chromaticity. And the polarization angle is, within the uncertainties, always parallel to the jet direction. And also, we found that there is little variability with time. So if you look at your constraints from the models, what you found is that there is only one of them that can reproduce the three different independent observables. The chromaticity, the variability, and the polarization angle can all be within the predictions of the energy stratified jets. So basically you have specific location for the emission of specific energies photons. And those are very likely due to shocks within the jet. When a blob is just colliding with another blob of matter within the jet, there is compression, and then you have emission of X-rays first, and then lower energy emission as you go further, go at further distances from the shock regions. And what we have done is that with IXPE, we have proven that shocks are responsible for the X-ray emissions within the jets. And it works very well for Marin 421, which is another high synchrotron peak blazars, but it doesn't work at all for the other, the low synchrotron peak blazars. So clearly there is something different here. Why first do they emit, do they have a peak in the infrared? And also, what is happening? How do they emit their X-rays? And we are still investigating that. We are still currently investigating, we are still questioning this. Just one thing, you know that those objects are variables. So we made sure that during the observation, there was no variation of the polarization, such as strong rotation of the polarization angle. But for Marin 4 to 421, we did many observations, and for some of them, we saw variation of the polarization angle. So we are also trying to understand what's happening there. Okay, supernova now. Another big source, class of source, because they are big, bright, shiny, and extended. And since we do imaging, it's very, very, very interesting for us. So I'm not a supernova guy, but I will try to summarize what we have found. Basically, at the high energy view of the supernova remnant is that when you have in the same picture the location of the TeV photons and X-ray photons, the morphology of emission are the same place, you expect to have inverse Compton scattering. The low energy photons are upscattered to high energy, to higher energies due to the electrons inside those regions. But if you have a decoupling between the GeV-TeV emission with little X-ray emission, then here you very likely have hadron acceleration from proton-proton interactions. So those are interesting theories because it helps you to understand the mechanism of acceleration of particles within the supernova remnant. And as we know, there are strong sources of synchronal radiation caused by relativistic electrons, and they are accelerated through diffusive shock acceleration. That's fine. It's basically non-thermal emission in the shell, and especially in the outer shell of the supernova remnant. Here you have simulations. And because we can do imaging with IXPE, we expected to be able to resolve the regions where there is particle acceleration, where the cosmic rays are produced. Because if you see here this is the total flux image of the shell of the supernova remnant. This is the polarized flux image and the polarization degree. You see you have blobs of high polarization degree, and this is where exactly there is particle acceleration and where polarization is created. And you see that you have a much higher contrast in polarized flux than in total flux. So what we want to measure is the direction and the level of turbulence of the magnetic field close to the shock region. To do so, we measured, we pointed IXPE towards Cassiopeia, a young supernova remnant, and we had a very disappointing observation. Basically, you see here all the pixels where we got signal at 1 sigma, and only 2 pixels with 3 sigmas. So it's very little to do science, very little to do something, but at least the 2 here, electric field vector, tells you that maybe the orientation of the magnetic field is at 90 degrees with respect to electric field vector. So the fields are radial at the shock region. And because we measured basically no polarization, which is a bit strange still, it very likely means that at scales lower than the physical scale of your pixel, which are 10 to the 17 centimeters, there is likely very much turbulence. And you have mixing of different signals, polarizations, which cancel out, and that's why we observed basically nothing. So, of course, we observed another one, Tycho, another young one. And what we have done is that we put almost 1 megasecond on it. And as you can see, the electric vector is much more well observed. And basically, it's very consistent on the shell with a magnetic field, which is radial with respect to the shock region. So again, 90 degrees with respect to those vectors. And this is interesting because the polarization degree that we measured is about 9% over the whole region and 12% at the rim. It's higher than the radio polarization, and it goes as high as 23%. In those maps, basically, are between 3 and 6 keV, 3 and 6 keV, because we are avoiding the strong emission lines, which are unpolarized, that would dilute the signal. This was the first localized detection of X-ray polarization from a young supernova remnant, and with a very strong hint for radial magnetic field. What is interesting is that because we are now able to prove the X-ray polarization and the location of this acceleration, we are able to look at what happened less than 100 years old. Those are fresh photons with respect to synchrotron emission, which is coming at much later time with respect to the photon generation process. So we are looking at freshly emitted photons, and we probe better the sources of emission and acceleration of particles. But probably the best of them was the SN 1006, which was also observed for 1 megasecond in twice in 2022 and 2023. And because it's such a huge source on the skies, the field of view of IXPE couldn't look at it once, and we had not enough time to do a mosaic. So basically, we looked at the brightest arc, and this is what we got. So it's a nice picture because it's from press release. You have here in violet the field of view of IXPE, and as you can see in the radio arc, we also have determined that you again have the radial magnetic field. Those are, for this press release, the magnetic field direction, so not the electric vector. That's why they are not 90 degrees rotated. And again, what we found is that basically the magnetic field are nearly parallel to the shock normal. And it's consistent with the quasi-parallel cosmic ray acceleration scenario. So it's very interesting. We are trying to probe this. But because this source is much older than the other ones, we also are currently looking at details of the cosmic ray acceleration in terms of environment dependence. And we have found differences between the young and the oldest supernova remnants. Okay, let's change and go towards accreting material, especially X-ray binaries, here with the micro-quasar. Cygnus X1 is a very bright and persistent X-ray source in a binary system with a 21 solar masses black holes and 40 solar masses star. They are located at about 2 kiloparsec from us, and the spectrum is very well determined. It's in a hard state where the emission from the accretion disk is dominating, not the emission from the jet. We have observed these sources with NICER, NuSTAR, Integral, IXPE, and a few other instruments. And this is the total flux plus in solid line, the best fit model, which comprises a disk, Comptonization, relativistic emission, relativistic smearing, and also non-relativistic reflection on the outer disk. Those are the components of the model, and it fits very well. We are very much able to reproduce the total flux of this X-ray binary. The polarization degree in Q and U parameters, the Stokes parameters to measure the polarization, as you can see, are different from 0. So polarization was detected. And it was not simply detected, it was detected with more than 20 sigma confidence level. So it's a very sure, very firm detection of polarization from Cygnus X1. And it brings extremely important constraints on the emission, the geometry of the emitting region, which is the X-ray corona. Around supermassive black holes, for those who don't know, basically for micro-quasar, you have the accretion disk that is emitting up to the soft X-rays, very soft X-rays. And for AGNs, the disk is colder and it emits up to the UV photons. But to create X-ray emission around the black hole, you need a corona. Basically, we don't know, a blob of electrons, very high, with a very high temperature. And those electrons are basically upscattering photons from the accretion disk to the X-ray regime, even up to the hard X-rays. But how do you create this corona? Where is it situated? What is its geometry? Is it stable in time? We have no idea. We cannot resolve this. And for many, many years, we had one very useful model in which you have the accretion disk, your black hole at the center. On the spin axis of the black hole, there is a lump, a blob, just a single blob, which is sometimes a bit expanded, but always in the polar direction. It's called the lamppost model. UV photons or soft X-ray photons are just being emitted by the disk. They enter the corona, which is on the spin axis of the black hole, upscattered. They go to the observer. It's the hard X-rays, from 1 to several hundred keV. And some of them fall back to the disk. There is reflection, absorption, and so on. It creates the Aaron-Gale line emission at 6.4. And this model had a very specific prediction for the polarization degree and for the polarization angle. The polarization degree should be low, a few percent, and the polarization angle should be perpendicular to the direction of the radio jet. But here we found the opposite. It's parallel to the radio jet. So what it means is that the geometry of the system has been completely wrongly underestimated. In fact, if you look at old realization of this kind of corona, you find that those lamppost model, which are here on the bottom, you see it could be the base of the jet, the base of the phase jet, or just a blob with a different extension on top of the on the spin axis of the black hole. The polarization angle is completely wrong. It's not at the right position. In fact, the corona is along the equatorial plane, not on the top. So our model that we are using for decades is geometrically wrong. Doesn't mean it's completely wrong. It's not rubbish, but the geometry itself was completely not understood. In fact, it's very likely like a sandwich corona on top of the disk, or maybe it could be within the truncated disk and the black hole. This needs to be further investigated. And this very, very important finding was also proved in AGNs. NGC 4151, which is a very bright radio quiet AGN. Well, we found out that the polarization degree is about 4.9%, but in fact, it has chromaticity up to 8%, almost at 6 to 8 keV. And the polarization angle also coincides, is parallel with the extended radio. So it means that if it's parallel, the emission itself must be perpendicular to the radio jet, so along the equatorial plane, along the accretion disk. And again, it evaporates the prediction, it evaporates the theory that there is a lamppost or blob, a spherical corona along the jet, along the spin axis of the black hole. So I will conclude here because I could spend many more time to discuss other sources that I haven't touched, Safer 2s, the Galactic Center, neutron stars, and so on. We got surprises everywhere. And what we can say is that polarimetry has changed and at least significantly improved our knowledge of high energy cosmic sources. We know, and we are now in a phase where models are lagging behind observation. For decades, we had plenty of theories and observations, and now the observations are basically almost all the time different to what we expect. So we need to refine the model. We need to understand better what is happening, especially for you supernova remnants, the different turbulence level, how do they impact the observed polarization, what is the magnetic topology in those magnetars, why are they different between magnetars. We know that X-rays are coming from shocks in the jet, but how do you produce those shocks exactly? The accretion disk physics must be rethought, especially with respect to the corona. And how do you bind the corona with the rest of the system in accreting sources? And again, it's the same for neutron stars, a word on them. Basically, we're expecting high polarization degree, and we got barely detectable polarization from neutron stars. So clearly, we did not fully understood how they emit X-rays. Foresight on the 2 years worth of experience, the magnetic universe is most of the time more polarized than expected. And all other sources, which are dominated by scattering or QED effect and so on, are much less polarized than what we expected. The secured targets were not as polarized as expected. And what is important here is that we need to couple the X-ray polarization measurement to other wavelengths observation, both including spectroscopy and polarization if available. And it's a critical thinking, a critical way to understand what's happening. And this kind of experience is basically paving the way for the next X-ray polarimetric missions, but also it opens a new observing window for gamma ray polarimetry, because now we need also gamma ray polarimetry to see what's happening at higher energies for those sources. One final word, IXPE in the 2nd of February will no longer be a private mission. It was, we had a consortium, we decided all sources and stuff. But starting from the 2nd of February, it's an open observatory. So everyone is invited to collaborate and send proposals for observations. So thanks for following this presentation. I will be happy to take questions.
Thanks a lot. Questions from the room and also from Zoom.
Okay.
Question. With the magnetar atmosphere, do you get Faraday rotation? I mean, I guess there's this ancient paper by Peter Goldreich and somebody where they say that, you know, a rotating neutron star has to have an atmosphere, and you must have a lot of electrons, rather extreme magnetic fields. So do the numbers add up to give you Faraday rotation?
No, actually, Faraday rotation, for what I remember from the different papers on magnetars and also neutron stars, from what I remember is that we didn't detect strong evidence for Faraday rotation in those sources.
Because that could explain the energy dependence, perhaps.
Could very well, yeah. But this in the resonant Compton scenario, also this energy dependence is strongly linked with the energy of the incoming photons, and between the soft and the less soft band. And it's to be honest, no, I think I don't remember mentioning the Faraday rotation measure, anything measured clearly. Nothing, we don't have a clear proof. But again, the magnetars that I showed are the two only magnetars which we have observed with IXPE, because we need very bright of them, very specific magnetic field intensity too. So most of them are basically not bright enough to be observed with 1 megasecond or less. Some of them needs 2 megaseconds, and in this case, it's simply too much. Within the IXPE consortium, we got per year about 20 megaseconds of observation, and there was 7 different topical working groups. Each topical working groups had few megaseconds per topical working group, plus some TOs and stuff. So clearly, they couldn't, in the magnetar group, they couldn't spend 2 or 3 megaseconds to observe the third object. They will try to do this during the observatory period of IXPE.
I have a quick one, 2 technical questions. So the first is on your last comment. So how easy it is to extend in energy the same technology? So can we go to hard X-rays and gamma ray with the same?
With this technology, it's fairly easy to change the energy range when you change the gas inside. You simply put a different mixture, argon DME, such as an example, can shift the energy detection from 2 to 8 to about 10 to 35 keV, but with almost the same efficiency. The only thing is that because the photoelectric effect is very efficient between a few keV and a few tens of keV, after that you will be dominated by Compton scattering, and in this case you need Compton scattering parameter. So there is a one soft spot, a soft energy, a few keV, well, from a few keV to a few tens of keV, where the technology is clearly the best, much more sensitive than anything else. But below that, you need to rely on crystal parameters, and higher than those 40 keV, you will need Compton scattering parameter.
And the other question I have is, if you go back to the laser result. So I agree, I totally agree with you on the fact that the models lag behind the current. If you can show this one. I think the model lag behind observations, and in particular, very few models compute polarimetry. But to me, I always had the feeling, but I'm not in the directly working on the field, that all the magnetic reconnection results were coming from peak simulation, basically, in which they only simulate very well the early stage of acceleration, and then everything else is an extrapolation.
Yeah.
So how confident are you about the like predictions for magnetic reconnection, where I mean technically there is no in the sense that there is no paper saying the magnetic reconnection for this polarization. They never produced. So how confident are you?
From the peak simulation, you mean? Yes. So I'm quite sure that the paper from which are extracted those kind of constraints are not from peak simulations, but there are more analytical models made by Alan Marsher et al. In the 80s, 90s.
But then there's still like some kind of extrapolation of results towards larger scale, because you never simulate the large scale jet.
Yes. What they do, if I'm not mistaken, what is do is that they have they just create a large scale jet, and they subdivide it into kind of voxels, so 3D pixels. And within each of those pixels, they put some kind of they put some ad hoc polarization depending on the physical effect they want to prove, and they look at the whole polarization of the jet, and they vary those voxels one by one or randomly and so on to simulate variability and to see how the full polarization react to this. There is maybe a question.
Okay, other questions from the speaker? Yes.
Yeah, well, just one quick to have an idea. What would be at the end of the 2 years? I think this was 2 years initial operation of the mission. The statistics of each type of sources that you would observe with enough time.
So what you mean? Like, how many AGNs, how many blazars, how many stuff?
At the end of the 2 years, how many of each type?
Okay.
Maybe you can imagine doing some stacking. Well,
so what we are currently doing is that we're stacking the background first. I know it's a bit stupid, but stacking the background is extremely important because it helps reducing the background on no images and higher significant detections. And also it tells us a lot about the polarization of the background along the galactic plane and also out of the galactic plane. And for those ones, point-like sources such as blazars and AGNs are extremely good. Stacking the data is extremely complicated because most of those sources are variable first, so you cannot stack the data. And we tried to do that. For MCG 52316, which is a safer to 1 AGN, so radio quiet, we observed it twice. And the fact is that we observed it at the beginning of the mission, at the end of the mission, and in between, we did some mirror realignment and stuff like that. And from year 0 to year 2, the spectrum, which from XMM and NuStar is exactly the same. In IXPE, there is a tendency to be a bit softer because of those mirror alignments. So clearly, the mission is too young to allow this kind of stacking of data. We need to extend it to get better understanding of the statistics on the problematic of the observations. And it took us more than a year to be able to do the aspect correction for imaging, because it was not always feasible to have a bright source in the field of view to basically correct the aspect of the images. So it was complicated. And clearly, one thing is that the NASA forced us to release the data, the reduced data, about 1 day, 2 days after the observation. So can you imagine the level of how can I say? Most of those data that were released after 1 or 2 days were basically wrong because we had not enough time to understand the statistic, to properly reduce the data. The technology is evolving, the reduction pipeline is evolving with time, the calibration is getting better with time too. So it was really a bad idea from NASA point of view. And basically what we intend to do is at the end of the second year, so basically in 2 months, we will reanalyze everything with the latest calibration, with the latest everything, background, rejection, algorithm, and so on, so that we'll produce final data. And after that, maybe we will get better idea, better statistics. If you are interested, we observed basically the galactic center twice. We observed radio-quiet AGNs also, 4 of them. A 5th one will be in January, NGC 1068. We observed about 12 blazars, half-half between high synchrotron peak and low synchrotron peak. We observed 2 magnetars, less than 10 X-ray binaries, 3 supernova remnants, and neutron star. We observed too many of them, and there is only very few people working on them. So basically, there are plenty of them that needs to be reduced, analyzed, and published. I don't know, more than 10 of them. And I'm quite sure I'm forgetting something here. But the initial goal was to observe within 2 years, 100 sources. Clearly, we are not at 100, but there are maybe half of it, maybe 50 sources, 50 different sources that have been observed at least, which is basically from, we just switch from just the Crab Nebula in the 70s to more than 50 sources, and it will improve with the next years. IXPE has been approved for an extension of 2 years, and we know that there is such a high pressure factor from the community that it will very likely be extended for 2 more years after that.
Other questions for the video?
How critical is angular resolution in some of the topics we discussed clearly for acceleration in supernova? It's a problem.
It's a problem, yeah.
You have mentioned some delay. Is it also a problem there, or?
It's a bit better, especially for the crab. We observe the crab too, and even though the resolution is not very high, it's also very modest. We are still able to see the main structure, so it's much better. But clearly, this is critical, as you said, for the supernova remnant. We will need much higher spatial binning, much better spatial binning to probe properly the sites of cosmic ray acceleration. But this is the best we could do at the time. So this is probably the only place where it's critical. Even for the galactic center that we have done, this spatial binning is quite enough to see the giant molecular clouds, which are reflecting the X-rays for the past outburst of Sagittarius star. The moon, we will try to do the moon also at some point, but it's so far also that so large in the field of view that we don't know yet what we will do, how we will do that. But we will look at the moon.
Okay, so I think if there are no more questions, thanks a lot, Frédéric.
Thank you.
So as always, we organize the lunch with the speaker, paid by the lab. So if people are interested to join, please let us know. We'll go probably into the rest of the program.